Hello friends, this is part 3 of solved paper PHYC1 of first semester Dibrugarh University 2023. Okay, I have already made 2 videos. Okay, and the playlist where these videos are added, that gonna appear at the end of the screen, at the end of the video, towards the end of the video. Okay, and do watch all the 3 parts. Okay, this is the 3rd part and I have already made 2 parts. And this is my Insta ID. You can follow me on Insta, ozhalekizit123, right? So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you. So now let's start. So today we're going to start from question number 3. So that length or distance and acceleration are invariant under Galilean transformation while velocity is not invariant. So this is already I have already made a video on this topic yesterday, I think. Yes, and I have given the link in the description box. I have written question number 3 and then I have provided the link of that video. Do watch that video where you're gonna get this answer. Okay, now let's move on to next question. So question number 4 is, what is conservative force so that conservative force can be expressed as negative gradient of scalar potential function? So now let me answer this question. So what is conservative force? First let me define that. A force acting on a particle, a force acting on a particle is said to be conservative, is said to be conservative if the work done by a force, here we're gonna write by the force, a force acting on a particle is said to be conservative if the work done by the force in moving the particle from one point to another point, from one point to another is independent of the path. So what does it mean? Suppose this is a particle, you are applying a force and it is displaced from A to B, and work done by the force acting on this particle, it should not depend it is moved through which part, this part, that part, doesn't matter. So work done by the force you have applied on this particle in moving it from A to B should be independent of path. So if you move this particle along this path or that part, the work done must be same. Then this kind of force is said to be conservative force, right? So hope you have understood this. Now let us prove that conservative force can be expressed as negative gradient of scalar potential function. Okay, so that means we're going to prove this force F is equal to negative gradient of V. Okay, so let me prove this. Let me take another slide. Okay, now here we're going to prove this. Let me take clicking here. Okay, now you see, if F is conservative force, is a conservative force. Okay, then work done by the force, work done by the force F, by the force F to another point, so just by the force F in moving a body, in moving a body, from one point, or from a point P, to another point, Q, is given by, now you see, suppose this is point P, this is Q, a body is moved by a force F through a very small displacement dr, suppose through a very small displacement dr, then work done by this force to move the particle through this small displacement is given by F dot dr, right? This is the work done. Then what will be the total work done in moving this particle from P to Q? That will be obtained by integrating this from P to Q, right? Hope you have understood this. So that's why integration from P to Q, F dot dr, that's what we're gonna have. And here you see, and now you see potential at this point, and this work done, work done in moving this particle from this position to that position, that's gonna be equal to the potential difference between these two positions. Okay, so here we can write Vp minus Vq, which is nothing but Vp is the potential energy of the body. So just wait, let me write here. Potential energy of the body at P. Just give me a second, just a second. Okay. At P. Okay, right? So, and Vq is the potential energy of the body at Q, right? That's what we can write. So now you see, if del V is the change in potential energy, just wait. Okay, now if del V is the change in potential energy, of the body when it is when it suffers a very small displacement, dr, okay, under the force F, okay. then we can write Vp minus Vq. This potential difference will be given by minus integration P to Q dV. That's what we're gonna have, right? So this dV is the potential difference, a change in potential when the body is displaced through a very small displacement. So when it is displaced from P to Q, then the change in potential will be given by dV. Change in potential means the potential difference between the 2 points, final and initial points, right? So hope you have understood this. Okay, this negative sign here, it indicates that we're gonna the external force will work against the force provided by the force exerted by the field. Field means, so it may be if it is a particle, it is moving in from one point to another point and of a gravitational field, then the force, the external force will work against the that gravitational force, right? So hope you have understood. That's why this negative sign comes here. Okay, so hope you have understood this. Now you see, let me take this as equation number 1, and from 1 what we can write, and from 1 and 2, this is 2 suppose. So from these two equations we can write this is equal to this one, right? We can write that because both equal to Vp minus Vq. Okay, so let me copy this one, right, and let me go to a new slide. So this one becomes equal to, now let me copy this, and that's going to be equal to what we have got, this, right? So how we have got this? From 1 and 2, from 1 and 2, that means equation 1 and 2, that's what we have got, right? Now you see what we can do here. Okay, this dV, here we have both, on both sides we have integration, so we can write this way as f dot dr, removing the integral, okay, minus dV. That's what we can write. Okay, minus dV. Now you see, just wait, let me take this one as equation number 3. Okay, so here you see dV, it can be written this way, del v by del x dx, right? Then del v by del u, sorry, y dy. If you have the knowledge of vector calculus, then you should know these things. Del v by del z dz, right? We can write this way. Now here you see this part can be expressed in this way, del v by del x I cap plus del v by del y j cap plus del v by del z k cap dot, just wait, just give me a second, sorry. Okay, this is dot, just one more second. Okay, equal to, this is equal to dx I cap plus dy j cap plus dz, just wait, let me write this one here. dy j cap plus dz k cap, that's what we can write. Now you see, if you take the dot product of these, then again you're gonna get this, right? And this can be written as here you see, here we have v. Now you see this part is nothing but you know del v, because del is nothing but del x I cap plus del y j cap plus del z k cap. Okay, that is v. So this is del operator, right? So that's why what we can do here, we can write grade v, okay, dot and this is nothing but dr. Okay, so therefore here del is equal to del x I cap plus del y j cap plus del z k cap, and dr, it can be written as dx I cap plus dy j cap plus dz k cap, right? That's what we can do. So dv is equal to this one, so which can be used here. Then from therefore equation number 3 implies integration, sorry, not integration, so f dot dr is equal to minus, instead of dv we can write grade v dot dr. That's what we can write. Okay, so this implies so let me write here f dot dr plus grade v dot dr is equal to 0, and let me copy this last step and let me go to new slide. Okay, so here you see, now you see this can be written as f plus grade v dot dr is equal to 0. Here dr is displacement is not equal to 0 in this case, so therefore what we can write, f plus grade v is equal to 0, so which means f is equal to minus grade v, hence this proved. Or you can say, or you can write this way, f is equal to minus grade v. Okay, here you can write this way, since this equation is true, okay, for all arbitrary infinitesimal displacement dr, right? And here you see, let me tell you one more thing. Let me go back to the previous slide. Here if you think that you can cut these two, then that's not gonna work. Don't cut this way. Here we have got dot product. Okay, so don't cut this way. So now let's move on to the next question. What is the next question? Here you see, determine the moment of inertia of solid sphere about diameter of the sphere. Okay, so let me show you this one, how to solve this. So moment of inertia of a solid sphere, about its diameter. First let us consider a solid sphere, and we need to find its moment of inertia about its diameter. This is the diameter, suppose, and here is the center. Let me draw another diameter which is mutually perpendicular. So we have to find the moment of inertia, suppose about a b. Okay, so let us consider its radius is suppose capital R, okay, and O is the center, okay. First let me write. So let us consider a solid sphere of radius R and mass capital M, having its center at O, okay, having its center at O, and its density be rho, okay. Let us consider its density rho. Now let us assume that this sphere is divided into circular discs, which are a very large number of circular discs like this, which are perpendicular to the axis AB, okay. So here we have considered that this is divided into large number of circular discs, okay, this kind of discs, okay, which is perpendicular to this AB, okay. And let us consider one such disc at a distance x from the center O, okay. Let us consider one such disc which is at a distance x from the center O, okay, and radius, we're gonna find the radius, okay. And here you see this distance will be definitely R, right? So what will be the radius? Here you see this is the side view, okay. If you see this one from this side, the front view will be like this. It is a disc, okay, so it must have a radius, okay. So hope you have understood this. Now you see, just wait. Now let us take this. So here is the center O, suppose, of the sphere, okay, and this is the circular disc, okay. This is the circular disc which is at a distance x from the origin O, okay, and this is the radius of this sphere, okay, which is capital R. Then radius of this ring will be given by, if you use the Pythagoras theorem, then that's going to be equal to root over R square minus X square, right? That's what we're going to have. So hope you have understood this, okay. So let the sphere, so let me write here, let the sphere be divided into number of thin discs, okay, by planes perpendicular to the diameter AB, perpendicular to the diameter AB, right? And let us consider one such elementary disc, T, okay, elementary discs of thickness dx, and at a distance x from O, okay, at a distance x from O. Therefore its radius is nothing but root over R square minus X square. right? So therefore the volume of this elementary disc, now volume of this elementary disc, okay, so its thickness, this thickness is, suppose we have considered dx, okay, its thickness is suppose dx, okay, so then what will be its volume? Volume of this disc, okay, volume of this disc. Now you see, you can consider this disc as a very small, a cylinder of very small height, right? You can consider this thickness as its height, okay, and the radius we have already got this one. So if it is a cylinder of very small height, this is dx, and this is the radius root over r square minus x square, then what will be its volume? Base area into height, right? Volume of cylinder is, volume of cylinder is area of one circular end into height. That's gonna be, pi r square. Instead of r here, we're gonna get root over r square minus x square and whole square, okay, into here height is dx, thickness is the height. So therefore what we can write, volume of, therefore volume of this circular disc, elementary disc, volume of this elementary disc is equal to its area of cross section, area of cross section into thickness, right? So that's going to be equal to area of cross section pi root over r square minus x square into thickness is dx. That's what we have got, right? And sorry, here I missed the square here, okay, so that's going to be equal to pi r square minus x square dx. So if this is the volume and we know the density is rho, then mass, we know that mass is equal to density into volume, right? We know these things. Therefore mass of this disc, so therefore we can write mass of the elementary disc, therefore the mass of the elementary disc is, let me write here, small m, and mass is given by the volume into density. Density is rho here and volume is pi r square minus x square into dx. This is the volume, right? That's what we have got. Now let me go to the next slide, okay. Now here you see we are going to find the moment of inertia of this sphere through this about this diameter AB. Now this diameter AB is passing through the center of this disc, okay, this elementary disc in two dimensional, though it look like this, but here actually what is happening here, this is the disc and the AB is passing through the center of this disc, okay. Hope you have understood this. And we know that moment of inertia of disc about an axis passing through its center, therefore moment of inertia of a disc about AB, which is an axis through its center, is given by so let me write the moment of inertia of the disc be suppose di. So that's going to be given by half, a circular disc of mass m and its radius is r, then the moment of inertia about this axis through the center is given by half mr square. So here it gonna be mass is here, we have got this. So here I am writing here small m, okay, because capital M is the mass of this sphere, the whole sphere. So that's why I am not writing here capital M, small m is written here, small m. Then here the radius is root over r square minus x square, right? That's whole square. That's what we have got. So that's why here half mass we have got rho pi r square minus x square into dx, that is the mass, and the radius is this one. So squaring this, what we have got, into r square minus x square. This root will be removed, okay. So this gives you, just wait, so this gives you half rho pi r square minus x square whole square. If you multiply these two, right, then dx, that's what we have got. Now you see, here you see, now we need to find the moment of inertia of this whole sphere. Now you see, this is the we have assumed that this is divided into large number of such disks like this, okay. So that's why we have to integrate this moment of inertia of this particular disks from A to B. From A to B means, here you see, if you consider this is the origin, O is the origin, the center of the sphere, then here we're gonna take this negative x-axis, and this one is suppose positive x-axis, right? This one is positive x-axis, and this point is B. So that's why we're gonna integrate it from x is equal to minus r to x is equal to plus r. This is x-axis. Just let me write the B here, okay, and sorry, this point is B, okay. So here you see, this point is x is equal to plus r. Let me consider that way. So to this side this is plus r, and to this side it is minus r. So that's why what we can write, therefore the moment of inertia of the solid sphere about its diameter AB is, so here we're going to write I is equal to integration of di, so that means integration half rho pi r square minus x square dx. So here it should be whole square, right? So we are integrating it from minus r to plus r, right? Hope you have understood this. So now let me take a new slide, okay. Let me take a new slide and let me copy the last line. So here you see, and in integration you must have got this property, that integration from minus a to plus a of function f of x dx, it also can be written as 2 into integration 0 to a f of x dx, okay. If we apply that, what we can write, so half into rho pi, this is constant, into 0 to plus r capital R square minus x square whole square dx. That's what we can write. So here this 2 and this 2 cancels, right? So what we have got, pi into rho, and here you see r is square is constant, and dx, integration of dx, so here integration of dx is x, okay, then minus, sorry, one more thing, just wait. So we can write this, if you apply a minus b whole square formula, then it's going to be r to the power 4 minus 2 r to the power 2 x to the power 2 plus x to the power 4. That's what we're going to get, right? So here we will get sorry, just let me write this way, integration from 0 to r. So here we're gonna get r to the power 4 minus, so let me write this positive term first, x to the power 4 minus 2 r square x square dx. That's what we're gonna have. Now if you integrate this pi rho, then r to the power 4 integration of so dx into this, if you integrate dx, then you're gonna get x, right? Then plus, if you integrate this one into dx, integration of x to the power 4 dx, that's gonna be x to the power 5 by 5, then minus, so this part is constant, integration of x square dx, that's gonna be x cube by 3. That's what we're gonna get, and we are integrating it from 0 to r. So now let's put upper and lower limit, then subtract. Then what you're gonna have in pi rho, then r to the power 4. If you put here r minus 0, then here we're gonna get r. So that's why it can be written as r to the power 5. Then minus, sorry, not minus, plus. So here if you put the upper limit, then you're gonna get r to the power 5 by 5 minus lower limit 0 to the power 5 by 5. That's gonna be r to the power 5 by 5. So r to the power 5 by 5, that's what we have got. Okay, so similarly if you put here upper and lower limit 2r square into r cube by 3 minus 0 cube by 3, that means what you're gonna get, you're gonna get r cube by 3, and if that is minus 2r square, then r cube by 3. That's what you have we have got. So now let me clean these things. Okay, so here it becomes pi rho into r to the power 5 plus r to the power 5 by 5 minus 2 into r to the power 5 by 3. That's what we're gonna have. And if you take LCM and simplify this, then you're gonna have pi rho into 8 by 15 r to the power 5. That's what we're gonna have. Okay, so now let me take a new slide. So here we have got I is equal to 8 by 15. So here I'm gonna write the 8 by 15 first, then let me write pi rho r to the power 5. That's what we have got. And also it can be written this way, that here you see 2 by 3 into 4 by 2 by 5, let me write here 2 by 5 into 4 by 3 pi r cube. I have written this because we know 4 by 3 pi r cube is volume of the cylinder, into rho into r square. That's what we have got. Now you see, if you multiply this 3, then again you're gonna get this, but here this part, what does it mean? This part is volume and this is density. So volume into density, that's gonna be mass, capital M, which is the mass of the sphere, right? So here you see, just wait, give me a second. Okay, so now what we can do here we can write that 4 by 3 pi r cube into rho is the capital M, which is the mass of the sphere. Therefore what we have got, I is equal to 2 by 5 m r square. So this is the required answer, which is the moment of inertia of a sphere about its diameter, right? So hope you have understood this. So now let's move on to the next question. So here you see, so same question number 5. Here we have, or determine the moment of inertia of hollow cylinder and solid cylinder about the axis of symmetry. So we need to find the moment of inertia of a solid cylinder and hollow cylinder about its axis of symmetry, means this axis, okay, right, which is parallel to its length. Okay, so moment of inertia of a hollow cylinder about its axis of symmetry. Okay, so first let us consider a cylinder, hollow cylinder. This is a hollow cylinder, but it has a thickness, and let me consider that its outer radius is suppose capital R, and the inner radius is suppose small r. Okay, so let me consider that way, right? And its length is suppose small l. Okay, let me take that. Now you see, let us consider a hollow cylinder and its axis of symmetry is along x-axis as shown in the figure. So let me take R is the outer radius of the cylinder and small r be the inner radius of the cylinder. Okay, so let me consider that way. Now let us divide this into large number of circular rings, okay, of external radius capital R, internal radius small r. Okay, let me divide this cylinder into large number of circular rings. Okay, so let us assume that the cylinder is divided into number of circular rings okay. So let me write here coaxial rings. Okay, coaxial rings, that means the same axis passing through the center. Okay, coaxial rings having the same internal and external radius, having outer radius R and inner radius small r, and their centers are on the axis of symmetry of the cylinder. Right, we have considered that way. So let us consider one more thing. Capital M is the mass of the cylinder, and small m is the mass of its ring, mass of its ring, right? So now you see, moment of inertia of the ring, moment of inertia of its ring, right? Of its ring about, and let me write here one more thing. The axis of symmetry is here x and x dash. Let me mention this. Okay, so let me mention this with just wait. This is x and x dash. Okay, so in a moment of inertia of its ring about x dash is equal to half m r minus capital R plus small r square. Okay, if the outer radius is inner radius is small r and capital R is the outer radius, then this is this gives the moment of inertia of ring with internal and external radii. Okay, so hope you have understood this. So in order to obtain the moment of inertia of this cylinder, we have to add all this moment of inertia of all the rings. Okay, so let me copy the last line and let me go to a new slide. Okay, so here is the new slide. Okay, now you see this cylinder is divided large number of rings. So if we add the moment of inertia of all the rings, then we're going to get the moment of inertia of this cylinder, right? So therefore the moment of inertia of the cylinder, of the hollow cylinder, about the axis, about its axis of symmetry, is is equal to sum of half m r square small r square, right? And here you see that's going to give you here we can write this summation m and capital R square plus small r square, right? And this is nothing but mass of, if you add the mass of all the rings, then you're going to get mass of the cylinder. So that's why you can get that half capital M r square plus small r square, where sum of small m is equal to capital M, right? So this is our answer. So hope you have understood this. So what if it is solid sphere? Okay, so in case of solid sphere, first note these things. Okay, now let us consider a solid sphere. So process is same, just here we have to make few changes, and let me show those things. Okay, so now let me go back to the previous slide. Here when we consider solid sphere, so instead of hollow, let me make it solid for the second part of this question. Okay, so we have already shown that how to find the moment of inertia of hollow cylinder. Now let me find how to find the moment of inertia of solid cylinder. So let me make here few changes. This, instead of hollow, let me write here solid, and if it is solid, then here we can write only one radius, and instead of this, let me write here radius. Okay, instead of outer radius. Okay, and this one will be divided into, instead of circular rings, here we're gonna write disc, circular disc having radius capital R, and we don't need the inner radius now, and centers of the discs are on the axis of symmetry. Okay, and here in this case the moment of inertia of each disc will be half mr square, okay, about the axis passing through their centers and perpendicular plane, right? So in that case we can obtain the moment of inertia of solid cylinder. So solid cylinder, and here I have to change this, so it's gonna be half mr square, right? So now here summation, here we're gonna get r square, then this will be only r square, right? So here this will be r square. This is for the solid cylinder. So hope you have understood this. So thank you for watching this. See you in the next video. Remaining questions will be solved in the next part. Bye bye, take care.